First of all, you need to locate your NMR file from the server. So we have an archive server as a map drive here, the Z drive in my case, ChemNMR, and we have the actual 400 megahertz instruments computer mapped to all the computers in the CAT lab. So if I open the 400, perhaps that's where your Spectrum was run, and go to data, and then data gives all the most recent files, you'll probably find your final year project NMR files under project. I'm going to use an example one from a former student. So I'm going to go in there into his NMR, and then it's reaction or lab book experiment number 16. And in there you'll see the file for the NMR. Within that folder, sorry, the folder for all the NMRs, within that there's several numbered folders. And they are things like the proton, the carbon, the COSY, the HMBC, and so on. I'm going to go up one and copy everything across to my C drive. So as I have it. You see, it takes a while because there's so many spectra have been run there, especially the 2D ones are very large. Right, that's on my C drive now. So I can move over to the ACD Spectrus Processor program and just use this open data window to locate it. So I copied it over to NMR example here. And there's the folder of all of the numbered files. And you see now ACD has recognized the type of file and told you that this is a proton spectrum, this is a carbon spectrum. Let's open the proton spectrum. Your version of ACD, so there's the spectrum opened. Your version of ACD might not look quite like this. That's because you can move these windows around. You can pop them out with the little arrow and put it somewhere else if you wanted. I could have it down at the bottom instead, but I like it up here, so I pop it up there. And I've got a chemical structure window open as well. Yours might be different. But here's the main proton spectrum here. If I use the wheel of the mouse, I can zoom in on the y-axis. If I right-click, I can zoom in on the x-axis, for example on this aromatic region here. And you see the peaks for the benzene ring in this compound. And again, the wheel will move that up and down. I can move along by going to the x-axis until the cursor turns to a hand and just dragging. Oh, if I just use the right mouse button down here, then it will expand or contract the zoom in the X direction, which is quite handy. So what we really want to do is characterize some of these multiplets and get J coupling constants and things. These two are definitely, these aromatic regions here are definitely multiplets. I can't really define them as doublets or triplets. So let's define them as multiplets. I'm going to use the manual selection peak analysis shortcut here. So I'll select that mode on the toolbar and just draw now with the left mouse button across that multiplet. And you see it integrates it for me, and because it's the first one I've drawn, it's given it an integral of 1. It's told me the centre of the peak at 7.48, and it's listed it down here, and it's called it a multiplet, so fair enough, it got that correct. I'll do the same for the other aromatic peak of my benzene ring on this compound. Not like that, I just zoomed in by accident. You can undo that with this undo zoom button to go back to where you were. So I want my left mouse button across that peak. You see that integrates to 1.49. Now I know those integrals are wrong because under here should be the ortho and para protons, and under there the 2 metaprotons. So I'm going to change that by right clicking on the integral number and choosing edit integral reference and changing it to 2 and pressing OK. And that's changed the other one accordingly to 2.98 or 3, which is correct for the 5 protons on my monosubstituted benzene ring. I can quickly go out to the whole spectrum by pressing this minus zoom button. And there we are. You'll notice this was quite a dilute sample because we've got a huge solvent peak here at 3.33. Now, this was run in DMSO D6. So what is that 3.33 peak? Well, there's a really useful paper in the literature, which I'll show you here. JOC 1997-62, page 7512, where they've characterized various contaminants in all the NMR solvents. So my solvent was DMSO, so it's CD32SO here. And you see that the solvent residual peak, where you have a single proton left in this deuterated version, comes at 2.5. And that can be useful for calibrating your spectrum. And that water comes at 3.33. On the next page, it's also got all the residues in carbon spectra, all the different solvents that you might have accidentally left in your tube without drying it or not have evaporated from your sample. That's a useful paper. So that peak at 3.33 is actually water. And the other really big peak over there, the one that was 2.5, is the residual solvent. And finally, if I move over to 0, I probably used a bottle of DMSO-D6 that already contained an internal standard, which in this case is TMS, tetramethylsilane. So this program has already shifted it so that TMS is at 0, and that puts the solvent peak at the correct position as well, and the residual water peak is correct at the 3.33. Now the fact that that peak is so enormous, because my sample is quite dilute, is going to cause us some problems when I use the multiplet tool, as we'll see. So it was alright for the aromatics over here. They got some numbers on. They didn't get these numbers. So over at the aromatics, what I can do to get the peak labels onto that peak is use this peak detection, peak analysis by peak level tool. I'm just going to change a setting in here so that it only applies to the zoomed area, the area that I can currently see, and doesn't affect the whole spectrum. So I'm going to tick that, and then I'm going to choose that tool and draw my line here. Now all the peaks above that line are labelled, and that's going to come in very useful when I move over to assign the smaller peaks as well. So I think I will just do all of those at once. So choose that tool again, make sure all of these multiplet peaks are included but none of the noise. Click it there, and you see rather than doing them one by one, it's now detected every single multiplet. And has it done a good job? Well, it got the singlet right, obviously. That is definitely a singlet down here at number 8 at 5.64. The next one should be a triplet, but it's included this whole thing as a single multiplet. So let me just zoom in on that. When I hover over it, there's a snip tool appears. In the current mode I'm in, that disappears in other times. If I was in this mode, oh no, there it is still. So I can snip that multiplet in the middle, which is what I want to do, and turn it into 2 multiplets. You see each one now integrates to 1. And it's got a much better detection now. It's worked out that the first one is a triplet and the second one is a doublet. See them being highlighted in the table below. And it's worked out that the triplet has a coupling constant of 5.78 Hertz. Normally you would have had to work that out by measuring the distance in ppm and multiplying it by the megahertz of the instrument you used. But they're all given now in this table. And the next one as well, it's a doublet, and it's worked out that the J value is 8 Hertz. Not only that, but over in this section, it's listed everything out, how you would have to report it in a publication. So you can copy and paste that straight into your dissertation at the back. But you should definitely check it, or perhaps get everything right in ACD first before copying and pasting that. So let's look at the next one. This doublet. It's got a coupling constant of 10.45 Hertz. It looks like it might be coupling to this one, which is roofing towards it. They're roofing towards each other. And it also has a J value of 10.45 Hertz. So if I now zoom out to the whole spectrum, notice it's labelled for me, the water and the DMSO-D6 peaks now, since I drew that line, because I've got that option selected to look for residual solvent and the NMR residual solvent. Let's zoom in again over here. It's missed off some of these peaks here, but I know that I can zoom in on that region and do exactly the same again. I don't want the noise, because these are just the satellites of the DMSO signal. Let's put that there. Perhaps I wanted it a bit lower. Actually, I've missed the edge of that peak off, so I'm going to zoom in on that and reset the peak detection level over here for this one. Zoom out, right click, zoom into my region of interest again, and that's selected all those as multiplets. You can expand those multiplets if they're not covering the right distance. It's not quite covered the edge, so I'm just going to go to the edge of that box and expand it over to there. And same that side, and then this one as well. It has nowhere near covered the entire multiplet, so I need to move that box right up to there. And you'll see the integration gets correct now, because that's just a single proton. What might happen sometimes is that a multiplet is incorrectly analysed by the software, the automatic mode, so then you'll need to edit it manually. This one did actually work, but I faked it to look like it didn't quite get the right multiplicity. This should be a quintet, but it's got it as with only 4 peaks picked. So I hover over the multiplet and right-click it, and press Edit Multiplet, which brings up my multiplet analysis tool. And while that's open, I'm able to pick that peak that didn't get picked. So if I hover over the peak until its value appears and click it, nothing happens. There we go, try again. Now we have all 5 peaks picked, and it has realised that there are sort of 4 spaces between peaks. It's got the J value of 7.29, and it's worked out that it is now a quintet. But sometimes that doesn't work. For example, imagine if it had decided that was a quartet. You see the lines drawn over the top? They're not in the right places. What you can do then, if I just zoom in, is follow this workflow. So we've done number 1, pick the peaks. They're all picked correctly. Number 2 is to measure the couplings. So I'll do all 4 of those couplings. So hover over 1 peak and drag to the next. And that would give me the first coupling constant. I can hover over 1 and drag to the next. It's the second coupling constant. And again. And then to the last one. And now the 5 lines are in the correct places for a quintet. That gets more difficult when it's things like a doublet of doublets or a doublet of triplets, but it can still work in the same way. The last thing you might want to do is assign the peaks. So you see here in the table, it's just got MO2, MO8 and so on as the assignments. Well, if I open up the chemical structure window, so that's this button here, it can either disappear or reappear and you can drag it in there. I can paste a structure in from ChemDraw. That's, I find, the fastest way of doing it. So copy that, goes to ACD and paste into that window. There it is. And the numbering is all wrong. You need to use the same numbering for assignments in your dissertation or your publication as IUPAC numbering. Now, because this is derived from a sugar, I would put this one, which would be the aldehyde peak of the sugar, aldehyde carbon of the sugar, as number 1. So I need the atom number renaming button, which has disappeared. Maybe it's here. Yeah, there it is. It looks like this. You can add buttons with that little drop down thing here. So the ones that are ticked are the ones that you can see in that toolbar. I don't actually need that show hide. I always leave them on, so I can get rid of that one. Now I can always see my renumber atoms. If I click that, I can decide to renumber all these things with some text before if I wanted, like H dash perhaps, or some text after, like prime or dash OH or something. But right now I'm just going to label them from 1. So I press OK. Now I'm in that mode, and I can click what was number 5, and it turns to number 1. Click that one, that's number 2, number 3, number 4, and that's number 5. Perhaps I want to number these. It might not be IUPAC. These should probably be 1, 2, and 3 prime. So I'll click the button again, twice, and I'll put a prime after. Start at 1 again, press OK. Now I'll choose that one to be 1 prime, 2 prime, 3 prime. Click the button twice again. And for the aromatic, I'm going to call these 2 prime. So that can be 1. Oh no, that's wrong. That should have been 2. So I'll click it again. It goes to 2. That's 3, 4, 5, 6. Now, if I want these peaks to be assigned properly, I need to ensure that Interpret Assignment is selected, which it was already. Let me zoom out and do one that I know. So I know that these are the aromatics. I know that these 2 are the meta. So while I'm highlighted and I'm in this interpret mode, I can drag, so hold down over it where the little yellow dot is appearing, I know I can hold down and drag over to the structure. And it's already suggested for me that these two orthoprotons are probably what this refers to, but I'm not sure if that's correct. I thought they were more likely to be meta. So I'm going to put them as 3 double prime. And it's automatically, because I've got that selected in the options here, assigned symmetric atoms. It's automatically decided that the opposite one is under that as well, which is true, because that's why it's integrated into 2. And then for the ortho and the para, ortho and para, I'll drag it over to be this one, because I've dragged it from the multiplet or from the structure. They both work. That's under there as well. And it's automatically done the other. So when I look now at my assignments in this mode, it hasn't labelled them as what I've chosen, 2' and 6' for some reason. Oh, there, it's done it now. When I've reselected the template that I want, Journal of Natural Products, it's updated that. Close. And it's assigning them as 4' and 2''. Ah, yes, this is right. So H-6''. So the peaks from 7.33 to 7.39. That multiplet is assigned to protons 6 double prime, 4 double prime, and 2 double prime. So this makes life a lot easier now for your publications. You can just copy and paste that in to the experimental section. If you want to have a copy of your NMR spectrum in an appendix, then you should generate it into a report where you can edit a bit more and then copy and paste it into Word. First of all, have a look at some settings you might want to adjust in here, such as View, Spectrum Labels. Do you want the assignments on? If I turn those off, I can't see the assignments on those aromatics, but actually they were quite good, so I'll keep those on. And then when I have it exactly how I want, perhaps zoomed into the region of interest, or perhaps you want to show the TMS peak so everyone knows it's calibrated properly, I can go to Report. There's a few options there as well that you might want to play with. I'm just going to try Standard. Press Report. And it should open up another program called ChemSketch. So there is the zoomed in region as I had it. It's also put the assignments up at the top. I don't need that, so I'll select that item and delete it. So just del. Let's put the structure in. Perhaps you'd rather draw that in ChemDraw because it certainly does look better than in ChemSketch. I'll get rid of that. If I select now the spectrum and press Ctrl-C, I can go to a Word document and paste it in. The best thing about this, rather than using screenshots or scans of paper NMRs, is that it seems to be bitmapped. So what I mean is if I zoom in, the detail increases as well. It doesn't just become pixelated. It's a bitmapped image, so it will print out, or PDF, really very clearly. And this is a publication, well, supplementary information, publication level quality. If I expand that picture this way, it does stretch it though, so I probably want to get it right within ACD first. So perhaps I'll make it the full size of a landscape piece of A4 and copy it and paste it again. And it's probably best if you have your appendix in the landscape orientation for all the NMR spectra. So I'll put that in landscape, paste it in, and so on the next page. And perhaps I would overlay a ChemDraw structure as well, and I can put a heading in and generate a really nice appendix there. It's put in my integral curves, but they have zoomed in too much, so they don't show anything. Those, I think they're red lines there. To change those integral curves to be a proper height, I need to go back into Processor here. I choose one of the integrals, one of the multiplets, by selecting it so it goes red. I might just zoom in on that area actually. And you see it's far too high. I just want to lower that by selecting the edge of the box and bringing it down. That will bring all of the integrals down. More appropriate to the reports. And now if I generate the report again, oops, sorry, back to the Processor. I want to zoom out and select the region to display and go to the right zoom level, like this. Those integrals, they're not quite right, are they? I still want them to go a bit smaller, so I'll choose an integral Bring it down. If you want the integral curves on, you don't have to have that, of course. Press Report. Now in the editor, those integral curves look really nice. And again, I get rid of this, get rid of the structure, select that spectrum and make it the full page. I could have turned off those integral curves just by selecting this object, right-click, Object Properties. So if I didn't want them at all, I could deselect them, and I've just got the integrations as the ranges underneath. And there's various other settings you can apply here as well. And that's it. Then you would copy that, as I showed, into your Word document. Delete that one. And it looks nice and clean. Finally, I'll just show you that ACD spectra can also be used with LCMS data, for example. So here's an LCMS spectrum. When you double-click this, it's going to import that data. It doesn't open it directly. It's just a normal LCMS spectrum. So here it's going to include the mass spectrum, chromatogram, and the diode array detector UV chromatogram. I don't need any of these things. I didn't do any of these fancy experiments. So press OK. And you see here, if I close the NMR, you can save this, by the way. I'll close it and it'll ask me to save it. So yes, I'll save it to the same folder. There's now a Spectrus file. Okay, now here is my total ion count chromatogram from that mass spectrum I opened, and a mass spectrum below. So if I click on this peak, it has this mass spectrum. That looks like it's some kind of polymer. If I click on this peak, it has this mass spectrum. On the UV chromatogram, oh no, it's just set at 254, so that's the UV chromatogram at 254. You can open IR spectra, Raman spectra, anything you can, any spectrum you can generate on an instrument. This program should be able to open it and allow you to analyze and manipulate it. Well, best of luck with your spectrum processing.